Hey everybody, thanks for coming. My name is Colt McAnlis and I'm a developer advocate at Google focusing on native client and gaming. And what we're going to talk about today is getting your port on, specifically porting your game to native client as of Pepper 18. So quick show of hands, who's already touched native client? Have you compiled the application before? Okay, cool. Put your hands down. For those of you, how many people have no idea what native client is or they've heard about it and want to learn more? And that's why you're here. Okay, cool. That's good. That allows me to kind of gauge how deep I dive into stuff. So Pepper 18 is the active SDK build as of right now. If you go to gonacl.com, you'll be able to get our SDK and see all the documentation that we're talking about today, as well as sort of some other amazing opportunities there. So let's get started. So it works. Native client allows you to run C and C++ code in a web page. Now this has been around as a feature set for a long time now, but the most important thing, and probably the coolest one about native client, is that no plugin is required. Now this is the kicker, right? I've got some statistical information sitting in a vault somewhere that shows that for some games, they lose up to 90% of the users that wanted to play the game as soon as they're prompted to install a plugin. 90%. Now, if you're an indie in this crowd and you've got a mortgage and a wife and a mother-in-law who thinks you're a bum because you're a game developer and not a stockbroker or something, 90% of those developers wanted to give you money. And they couldn't because you asked them to install a plugin. So the goal here is if no plugins required, that's fantastic. And if you're one of the programmers who's worked in the games industry for the past 30 years, chances are you've got 30 years of C++ code sitting around and 30 years of experience in C++ code sitting around that can now migrate to the web, which is amazing, right? Developers spend billions of dollars cultivating this technology, and to get to the web right now, they have to throw it away and rewrite it in some other scripting language. But if you can use the direct code, this is fantastic. It allows you to leverage your existing technology to move into this new marketplace. So here's the gist, right? It all starts with your C++ code. Native Client provides in the SDK a version of a GCC and a G++ compiler that produces safe, portable x86 code. This is provided in the form of NXEs, or Native Client EXE, right? In addition to this, we'll produce one for 32-bit and 64-bit architectures, as well as an NMF file, or a Native Client manifest file. The manifest effectively lists which architecture goes to what file path for what executable, right? So if it says if you're running a 32-bit, point to this executable. If you're running 64-bit, run to that executable. You embed this information in an HTML file using this small little tag right here. So you make an embed element, you name it, you give it a height, you define your manifest. You point to the manifest, not to the NXEs, because remember, the manifest defines what NXE to use. And then you set an application type right there. Once you do this, you've gone through this process, you've compiled it, you've embedded it in a page, and then you load the page up, and boom, you see some amazing graphics on the screen and some stuff that you traditionally don't see in a web game. This is actually a screenshot from an Xbox 360 title running in native client that was ported in about 3 months. That's amazing technology to see post-processing and full screen blend and skinned animation and color tint and all this just great stuff there that you have access to now. So let's talk about the first steps, your GCC and your G++ compiler. So to use these, if anyone here is a Linux developer, then you're very intimately familiar with GCC and G++. If you're a Windows developer, this is kind of new ground that's kind of awkward and uncomfortable for you. But first off, to get your code compiling in GCC and G++, you have to make sure that it's ISO and IEC compliant, which effectively means it matches these protocols and these standards. Now, it's probably not best to go look at these standards and figure out the mapping. It's probably actually best to try to compile your code in GCC, figure out what it complains about, and then iterate that way. Predominantly, this standard defines POSIX-style coding and functioning. So it uses syntaxes like p-threads as opposed to begin and end thread, as well as conditional variables rather than mutexes and other things like that. In addition, this compliance standard, and this is the important one, does not define any OS-specific calls. So you can't access the registry from GCC, right? That doesn't make sense. You can't open up a direct video stream using direct media. That doesn't make sense either, right? So you need to make sure that your code is platform independent and uses these POSIX style calls. The GCC and G++ compilers also do the amazing thing, and this is sort of the linchpin, right? Like it removes any unsafe code. This is the whole point of native client. The whole point is to execute safe, portable assembly language code in a web browser. Security is of the utmost importance here, more than performance, more than anything else, although we are amazingly performant, and I can give you those numbers offline if you're looking for it. But it removes all of this unsafe stuff and creates this nice little package that can run and execute in multiple places. And so once you get this code and you're saying, okay, this is cool, I have the ability to execute this code, how does it actually interact with the system? So to understand how native client gets access to these system level resources, I have to take a step back and actually talk about how Chrome, the web browser, gets access to these system level resources. So a long time ago, a company made a plugin architecture called NPAPI. Effectively, this plugin architecture allowed plugins to be developed for a browser that then had access to lower level systems in various ways, so that users can install the plugin, and if the plugin DLL targeted these header files, it had access to these things. Well, the problem was that at its heyday, this NPAPI architecture was actually the #1 problem of malware and bugs in the environment. So Chrome went ahead and said, we're going to support NPAPI, but we want to create a safer version so that we don't have to worry about all these sort of pop-ups and spyware and malware. So we created what we call the Pepper API, or PPAPI, which is a plugin architecture that allows you to target FileIO, rendering, audio, and even have the ability to communicate back to the page that's hosting the plugin through JavaScript post message results. So understanding this, that there's effectively a Pepper API that allows plugins to access these inner workings through Chrome, native client is effectively a module that communicates with this. So your NaCl file, when you compile it, you'll target these specific headers to do things like FileIO, audio rendering, and JavaScript. This is how your program gets access to the lower level architecture. And now it's worth noting this too, is that the Pepper thread is actually running on the main thread of Chrome, right? So your native client module is sitting there doing execution. Also on this main thread, though, are some other important buddies that you need to be aware of. First off is WebKit. WebKit executes on the same thread. This is the layout organizational DOM rendering style engine. It's out there, open source. Also V8, which is Chrome's virtual machine for handling JavaScript, as well as some other fun stuff like WebRTC audio processing, video, and all this other stuff. The important takeaway you should say here is that your native client module has the ability to effectively stall out this main thread if not doing correctly, right? So if you go in and put a spin loop on your main thread, you're effectively going to halt the entire web page because the WebKit doesn't get the input processing and V8 doesn't get JavaScript processing. So it's going to stall the tab and effectively crash out. Because of this, you're not supposed to call any blocking functions on the main thread, right? Like this is a bad idea. So none of your code should be calling blocking functions on the main thread. And because of that, the Pepper APIs are all asynchronous, right? None of them are blocking at all. This means that you can call a Pepper API from the main thread, and then sometime in the future, you'll get that result. Generally, that's about 1 frame. So if you looked at that previous diagram, you can see that we've got WebKit, we've got V8, and then we've got NaCl and some other stuff. So if NaCl says, hey, I want to go load this file, it's going to kick off a request. And then we have to generally wait until WebKit V8 gets processed and the plugin frame gets processed before those results can be given back to the main thread of your native client module. Also, one of the restrictions of Pepper is that all the Pepper APIs must be called from the main thread right now. This is a current restriction that our team is actively working on to fix. But this has some potential downsides that you need to be aware of. Before we dive into that, let's talk about how this works, right? So on the top here, we've got a function that shows how to do FileIO, right? So we've got a function, we're asserting that this is coming from the main thread. We get some information from the user, and we actually call FileIO.open. With FileIO.open, you actually provide a completion callback. The completion callback will occur once this file open request has occurred at the lower level, the Pepper API level, and the results of that will be pushed back to you. That's the second function here you can see, fopen callback, right? This will get called on your main thread once everything's been done in the lower bowels of Chrome and the Pepper APIs. And then you can, do some stuff, show a cat, issue a read, whatever you need to do at that point. So this is sort of a problem, right? Because this works in a very different way than all of your architectures. This is not how your game engine is designed. I can guarantee this is not how your game engine is designed. Even if you have asynchronous loading in your game, sooner or later you're going to expect fread as a blocking function, and you've got everything working around that. More importantly, you probably have fread calls coming from the main thread, which in general is a problem, right? So the problem, the point next is how do you design around this, right? How do you beat this? How do you say, how do I touch my code? Well, one idea is to, modify all of your freads to use this blocking callback system, or how do you do these other things, make sure the thread doesn't stall. Forget all that. I'm going to give you the shortcut. I'm going to drop some wisdom on you. I'm going to point my knowledge cannon in your direction and give you a blast of info, right? The best idea is to actually spin up a thread and run your main game logic on that thread, and leave the original main thread as the pepper thread. Basically what this allows you to do is you wrap all of your platform functions to issue communication back and forth to the main thread. Let's take a look at what that looks like here. So your game has the pepper thread, or the main thread. That spawns off your logic thread. The logic thread is effectively going to run the main loop, while true, update, render, network, update, network, render, do all that stuff, and it's going to just continue doing that on the logic thread. The pepper thread is the only access to FileIO, JavaScript, and audio. Your logic thread should not have direct access to that. Instead, the logic thread will call specific commands, which pushes a function to the pepper thread, and then it will block. The pepper thread will then receive that function, communicate off to the lower level I/O, do its fun stuff, return that data to the pepper thread, and the pepper thread will then return that data to your logic thread in the fashion. What this means is that you can overload fread, fwrite, blocking functions like that to effectively do the same thing that you would expect them to already do in your game, right? You just effectively create this abstraction layer around them so that it actually communicates with the pepper thread in a proper manner without actually having to touch all the lines of code that you've already got written. Here's an example of how to look at this. So this top function here is request and wait. So what this will do is assert that, first off, you're not running on the main thread, you're running on a worker thread. And native client and Pepper actually provide a nice little API that will auto-call your function on the main thread on your behalf, so that you don't have to write all the intricate threading and messaging and queuing logic to get it to call there. So simply you call module.get.core, call on main thread, and you effectively pass it a callback function. And this will ensure that your callback function will get pushed into the proper queues, and it'll be called on the main thread the next time a frame process happens. Now, what's nice about this is that this allows you on the calling thread to then set a conditional data variable and sit around and wait. So with this function here, you actually issue a function command, wait until it's been called and executed on the main thread, and control has been returned, right? And you can see on the bottom here, this is the return from main thread function. Effectively, what this does is first off asserts that you're on the main thread, because you want to make sure your code's clean, you want to make sure you're doing the right thing. And then it'll actually get the information that's been passed to it as a callback parameter, set some result, and then signal the conditional signal. That signal right there, that event, that pthread conditional, will allow the worker thread, the logic thread that actually issued the command, to then wake up, continue doing what it was doing, and move on. This is fantastic, right? With these two little functions right here, you can implement a structure around it that allow you to overload fread and fwrite and those other functions to be blocking functions from the logic thread. So this is effectively what happens, right? You end up in a situation where you start calling data, it blocks, comes back, calls, data, blocks, come back. And this is fine for a lot of sort of functions that you expect to work this way. Your architecture will transition over seamlessly and you won't have to worry about it. The problem turns into function APIs that don't benefit from working in this fashion. For example, rendering, right? Rendering works very differently. Rendering expects that I shouldn't have to block for lots and lots of frames to submit each instance, right? In that situation, what you want to do is for these types of calls that are best for fire and forget, that you don't actually wait for a response. These things don't need any information back from the main thread. As such, you should just fire them off very quickly and allow the logic thread to move on. So you can see here you get 3 fires really quick, and then the pepper thread spends its time doing the proper resource handling to the underlying architecture without you having to block. Now for rendering, there's actually a different process involved here that you can actually think about in a different way. A very modern graphics engine mechanic is actually the concept of buffering up all of your draw commands, submitting them off to the pepper thread in a various form so that it kind of gets the entire frame, and then it starts queuing through it properly. So what happens is your logic thread will go and do the rendering, actually create the calls. But instead of actually doing the rendering and calling the APIs, what happens is you overload the API to create a small little representation, like a quad word or some form of it, that gets pushed into a FIFO. And that FIFO is then consumed by the pepper thread and issued off to the appropriate engines below that. Now this is important, that what you're effectively doing here is you're creating a waterfall processing method, or a producer-consumer FIFO, between your logic thread and your pepper thread, where the logic thread will do logic frame n, kick off the rendering results for that, and render thread will then do render frame n while the logic thread moves on to the next frame. This, again, is a very common paradigm for next generation consoles, Xbox 360, PS3. This is what you're doing in a lot of your systems right here. Traditionally, they call the pepper thread the render thread at that point, and there's some variation of what data is pushed between the two. In this particular method, you want no logic occurring on the Pepper thread other than just rendering your data. So that's the ecosystem that you're in. That's sort of what you're dealing with. Basically, what you need to do is spin off a logic thread and then modify your code such that you handle two different types of calls. You've got the calls that require feedback from the Pepper thread, and in those you need to block and wait for that information to return. And then you've got the fire and forget calls. And those are the calls that you just either issue immediately and then keep moving on, or you bundle up into some sort of frame or boundary mechanic and submit in one batch, and then let the Pepper thread do its thing while your logic thread moves on. So once you understand the environment that you're in because of the Pepper API restrictions, which are temporary, by the way, now you can actually start porting the rest of your code. And this involves understanding at a number of levels. So let's dive in. The first is FileIO, right? So if you've never developed a web game, let me clue you in on some specific information. You're going to put your HTML data and your NIXI data and your NMF data on some server somewhere. And when the user loads your page that embeds this module, it's going to be received by the client and auto-cached by Chrome on your behalf. This is just going to happen automatically. And it'll grab the HTML data, the NIXI data, and the NMF data and cache it for you because it's defined in the embed tag. Now this is great, right? This means that Chrome is handling your caching on your behalf. You don't have to do anything else. You just kind of sit back, hands behind your head, allow it all to happen, and it's good to go. The problem is that there's other data that your game needs. There's zip files, for instance, zip0 and zip1. These will not be pulled down automatically for you when the user loads your page. Instead, for these, you have to use a getURL API inside of Pepper or an XHR request inside of JavaScript. And that'll pull down these binary assets. Now the cool thing is that with this call, with the getURL call, it will also cache itself in Chrome on your behalf. So you can actually fetch these zip files, Chrome will cache it, and then the next time the user asks for it, it'll already be in the cache, and they can get it from there as opposed to going back to the server, which is a longer round trip, right? One of the interesting things about this, though, is that when your data is in the cache, it can also be evicted from the cache at any single time. Right? The user can go load a website which uses more data, or they can clear the cache themselves. But basically, they can purge all of this asset storing that you're doing on their behalf so that the experience in your game is not as optimal as it should be. And this is a bad thing. To answer this, there's actually a cool little API inside of Pepper called the FileStore API. The FileStore API will allow you to grab data inside of the client's memory and store it to a persistent, sandboxed, obfuscated file store. Now, this data will exist on disk until one of two things happens, or both will happen. The user navigates to this sandbox system somehow through their API on their operating system and manually deletes the data, or your program deletes the data. So effectively, this allows you to take control over the caching mechanisms that are used during this transfer process. So definitely make sure you're using that. You can click the link at the bottom here for more information. That actually directs to gonacl.com. We have a specific article on how to do all this. FileIO and shutdown. Console developers in here, you will help me lament over the process of trying to write to a memory stick that's been pushed into a console, and as you're writing, the user rips the stick out because they think it's done. And then all of a sudden you have, effectively the world explodes, right? The data written to disk is corrupted, the information being transferred is corrupted, and the user is mad at you because you didn't know they were going to rip the stick out. Now, who knows? Well, anyhow, in a web page, you have the same problem, right? When you're trying to write data to your persistent file store, the user can tab away, they can close the data, a crash can occur, something can happen that effectively does the same process. It effectively deteriorates the data, stops the write, causes problems all of sorts. So if you've actually opened this file and tried to write to it, when you try to load it the next time around, the information is going to be corrupt. Basically, you're going to lose it. The better methodology here is for any writes to file, what you actually want to do is write to a separate file or a duplicate file and communicate all of your data there. And then once all of your writing has been finalized, at the end of your process, you actually then rename some process over to the intended position. And this means what occurs here is that if the chance that the user corrupts the data during the write to the persistent file store, that it doesn't actually corrupt the original data on disk. So that when the user loads the game next time, all they've lost is the delta between the last time they've saved, as opposed to your entire save file, which is a good thing. Now, for those of you who are doing FileIO, there is a really cool mode that's recent, that's actually dangerous FileIO. And there's some terminology about why you want to call it dangerous or not, but this is really helpful to those of you who are developers. So in developer mode, you can actually write directly to disk outside of the obfuscated sandbox. This is really helpful, right? Effectively, when you launch Chrome, you can set an environment variable, NaCl dangerous enable file access, and then you run Chrome with no sandbox. This effectively turns off some of the security handles that you have available to you. And then in the code, in your C++ code, you actually do a direct fopen and start writing to it. And what this will do is actually create a file in the application location of where NaCl is. So for instance, path to Chrome /build numble, and that's where native NaCl.exe exists. So with this setup here, this actually creates a tracelog.txt in my application folder for Chrome 19, which is currently in Canary. This is amazing, right? So for those of you developers who are trying to do inline profiling or trying to dump crash disks or crash logs to disk in these sorts of fashions, having to wait for the asynchronous file system is just not doable, right? Instead, you actually want to control writing directly to a disk, and this gives you that ability. This is really important. It allows you to move forward with getting all this stuff done. And you can click that link there for more. It's got more information on it and how you use it. Rendering. So first off, native client uses OpenGL ES 2.0 as a rendering API. So this is the same API that's used on mobile devices today. Porting your game to use this is step one, right? So if you're using DirectX, you need to port your stuff over to OpenGL first, because that'll be an easy transition for you. And then from OpenGL, you need to move to OpenGL ES 2.0. You can do this using a project called Angle on Windows. If you click that link, there's a source code repository there where the entire source code's available. Effectively, Angle is a DLL suite that provides OpenGL ES 2.0 headers that you can then target that will translate to DirectX calls internally. So you can effectively test how your code is working and do this all on Windows. To note, there's no OpenGL ES 2.0 runtime on Windows. It doesn't exist. So if you're going to try to test this on Windows, you're going to need to use Angle. Specifically, you need to note that OpenGL ES 2.0 is not OpenGL, right? There's a stricter set of compiler rules, and this is because we need to make sure that security is step one for the end user. The developer, your experience that you're trying to communicate, that's all fine and dandy. Keeping the user safe is more important than all of that. And not all the extensions are available, right? So for instance, if you're expecting instancing or access to a specific tessellation shader, they're just not going to be there, right? This is an API that's handled by the Kronos group, and then rolling the feature sets out is sort of tiered because we have to go through those bodies. But make sure that you understand that OpenGL ES2 and OpenGL are not the same thing. Specifically for API nuances, right? For instance, in OpenGL, you can create a compressed texture and not pass any information into it. So you can just say, hey, create this blank texture and I'll fill it in later. OpenGL ES 2.0, actually, this is considered an error. If you try to do this, it'll actually crash. Now, the problem is this is not well documented. And if you go to the native client forums, you'll actually see about 10 or 11 people, myself included, complaining about this problem and asking for a solution. The reality is that this is an OpenGL ES 2.0 spec that is not compatible with OpenGL. Make sure you test all of this stuff properly. And definitely make sure you're checking the API before you start blaming native client, because a lot of the times the problem's there. So the next thing you need to be aware of when you're doing rendering is that you're actually rendering from a sandbox. Now, because of security issues, we don't actually allow your code to directly go to the driver. We don't actually, when you do a set command or a draw command or anything, we don't actually go right to the API. Instead, what occurs is we have a separate render process. The render process is responsible for handling all the interaction with the API. Nothing else goes through this render process except API calls. Now, to get from the Pepper thread to the render process, though, we actually create an RPC buffer. Now, what happens is the Pepper thread will push commands into the RPC buffer, and then that buffer will be flushed at some time later to the render process. This basically creates about a frame of latency between a producer and a producer-consumer FIFO that you need to be aware of. What happens with this producer-consumer FIFO, though, is that your RPC buffer sooner or later will get full, right? So what happens is you draw an object, you update your vertex buffer, you go to draw an object again, and the buffer's full. So then it stalls. What happens here is you hit something called a flush sync, or a sync flush, depending on which documentation you get, right? What happens here is that the process, even though you're not done with your frame, right, will actually halt, and it'll say, hey, we're done here, I'm full, and it'll actually issue a flush sync. Now, what'll happen here is that it blocks the processing and calling thread until all of the data inside that RPC buffer has been consumed by the render process. What this means to you is you'll start seeing 30 millisecond spikes randomly in your game, hitches in weird places. When you start debugging and profiling down into it, you'll see random calls all of a sudden taking 30 milliseconds. And to you, this is going to be maddening, right? You're going to try to figure out why this one draw object is taking 30 milliseconds. Is it the pixel shader? Is it the number of vertices? Yada, yada. You'll start moving the thing around and noticing that it never happens on the same draw call, that it happens sort of as a temporal problem. And what the real problem is that the RPC buffer is getting full. So make sure you note that ahead of time. Now, how you combat this is kind of interesting. First off, swap buffers actually kicks off a GL finish call on your behalf. GL finish will actually force a flush to occur of the RPC buffer. So you fill in a frame, you hit swap buffers, and then you start filling in the next frame. That swap buffers will push everything off to the render process on your behalf. The goal here is to implement these flushes in strategic locations inside of your render loop so that you never hit a sync flush, right? So effectively, what you're doing is continuously pushing the data and forcing that RPC buffer to flush so that you never hit these 30 millisecond waits, right? So you need to do is, once you draw some stuff, you insert a flush, you draw some more stuff, and you insert another flush. Now the key here is that figuring out where to insert these GL flush calls, right? Like that's the trick. To do that, what you have to do is you have to go back and analyze your frame. You got to take a look at where the heavy spots are, where you're hitting your flush sinks, and then figure out, hey, I need to insert a GL flush manually before I hit that point to save me 30 milliseconds. Basically, what you're trying to do is keep that RPC buffer continuously moving to keep your frames from getting stalled out. So once you understand how all this works and how you're rendering, how the rendering occurs, and how the rendering happens between the Chrome and native client module and the rendering process, you need to take a step back and take a view at the bigger picture, which is 3D in the web. 3D APIs, as well documented, can be malicious on the web. As much as we would like to admit it, the web is homogeneous, but GPUs and hardware are not, right? You've got a different machine, you've got a different machine. Heck, my coffee cup has a different GPU processing in it than any of you, which I think this is a 9800, but we'll get back to that later. So the problem here is that because of the fact that some of these drivers can be malicious, WebGL actually has a list of blacklisted 3D drivers. Most of the time, if a driver has a problem, we can say, hey, here's the problem, submit it to the vendor can fix it and push out a patch to it. In the situations where this doesn't occur, we effectively have to say we have to blacklist the driver because this is a malicious piece of software that can cause problems on the end user's machine and expose them to potential security risks. And because of that, the user can hit a web page and we could say, hey, you're not allowed to run WebGL, you're not allowed to run OpenGL inside of native client. And to detect this, effectively what happens is you fail to create a context. That's the basic thing. The first thing you do in any OpenGL style system is you create a GL context. When that fails, it means one of two things. Either the user doesn't have the proper hardware to run any WebGL or OpenGL, or the user has a set of blacklisted drivers. Your job is to detect this and respond very early, because I'll tell you, nothing's more annoying than a user spending an hour and a half trying to get your game to run and updating drivers and updating Chrome and doing this and that to finally get down to it and realize the problem is they needed to go update a patch or they just can't do it in general. Make sure you update this early and tell the user so that you can save them all that time. To do this, it's actually really simple. Here's a little snippet of code that you can use in JavaScript. So this is way before native client even loads, right? So the user loads your page, you're going to execute this snippet of JavaScript to determine whether or not the user is blacklisted first, okay? Basically what you do is you try to create a WebGL context. If that WebGL context fails, you can alert the user immediately that they either have blacklisted hardware or they don't have hardware sufficient to run this. If it passes, then you know that the user has a system that can run your game, your 3D game. And you can also do some other cool stuff here. Since you have the context, you can go ahead and test additional extensions. Like, does the user have occlusion calling? Or does the user have the ability to run 4096 by 4096 textures? You can do all this in JavaScript before you start loading all of your nexes and start transferring your binary data from the web. This is really cool to do. The link at the bottom here actually links to a specific example of how to do all this, as well as you should take a look at the load progress example in the SDK. It has this as well as a fleet of other tests that you should be doing, as well as detecting download process and displaying that to your user. So make sure that that's part of your best practices. Working in a browser. So you understand the environment you're in. You understand the hitches and the hurdles that you're going to have to jump for FileIO and rendering and all the problems associated with that. So now let's talk about working inside of a browser. So this has less to do with your technology and your code and more to do with the ecosystem that you're living in. So first off is NaCl whitelisting. Native client is not enabled inside of Chrome until an action occurs, right? This is for a number of reasons, predominantly security, right? If there's an issue in native client that we're not aware of, we don't want malicious code just sitting around on the internet. We want some way to make sure that random users are not at the mercy of a problem that we find. So native client is not enabled until one of two things. First off, for developers, you can turn on native client via a flag in the About Flags page, right? So this will allow you as a developer to get access to any native client content that exists on the web. For users, though, you don't want them setting a flag. Users have to go through a different path. They actually install the game from the Chrome Web Store. And what happens here is that the Chrome Web Store will actually list the origin that you've specified for your NaCl module. So basically where it's resting on a server. So I've got a website, mainroach.blogspot.com, right? And I host my native client app there. When I create my Chrome Web Store instance, I say that my native client application will be hosted from mainroach.blogspot.com. When you install that as a user, that origin, mainroach.blogspot.com, will get listed inside of your preferences as a whitelisted location. Hey, it's okay to serve native client content from this location. And note that the NMF and the NIXIs must be loaded from that location. You can put zip data in different places and OGG files and JavaScript all on a content network, wherever you want them. But the NIXIs and the NMFs must exist from that whitelisted origin. So once you've done that, you have a pretty easy way to test this, right? So you can actually determine beforehand whether or not the user actually has native client enabled or available to install. So first off, you need to detect whether or not the user is running Chrome. As of today, much to my dismay, Chrome is the only one that uses and installs native client. So first off, to determine if a user can run native client, you need to detect if they're using Chrome. Secondly, the Chrome Web Store has a really cool API called window.chrome.app.isInstalled. And you can define in this whether or not the application defined on this page has been installed from the Chrome Web Store. Now, because an end user has to install a native client application from the Chrome Web Store, this is effectively your test to determine if the user can run it. So if some user randomly browses to your web page that doesn't have native client installed or hasn't installed it from the web store, you can detect it here and direct them to install it. You can also use something called inline install, which is a great little nifty feature from the Chrome Web Store too. But the important thing here is that you need to detect this and tell the user, because otherwise they're going to browse to your website and then they'll get a plugin request. They're going to be like, hey, what's this? This is crummy. I'm going to give you 0-star reviews and send you pictures that you don't want to see. Definitely click the link at the bottom of this slide and also check out the load progress example in the SDK for more on that. Now, for developers, it's worth pointing out that the Chrome caching mechanism is both aggressive, amazing, and magical. How well it caches data and how aggressive it is at keeping it around to make sure that you're always hitting the cache as opposed to going to the web is really a thing of beauty. The problem is, for those of us game developers who do test, launch, and iterate patterns, this is a problem, right? Because as I change some code, deploy it to Chrome, and then iterate on that content, I want the latest version. I don't want the cached version. To get around this, because Chrome will bite you in this manner, you can actually go to the developer tools and actually turn off caching. You can disable caching so that Chrome will always try to fetch the most recent version and won't ever try to grab the data from the cache. Now, it's worth pointing out that you probably don't want to do this on the version of Chrome that you're running every day, because otherwise your browser will just slow down in general. But make sure that in your developer version of Chrome that you're doing it like this. Now, also while you're developing in Chrome, there's a whole fleet of tools that will help you in your development. And these are called the Chrome Developer Tools. You can click the link for the more expansive declaration. But effectively, you can click on the wrench, go down to Tools, and go to Developer Tools. And this will launch a small little bar at the bottom of your window that has a number of options here, right? Elements, resources, network views, etc. One of the cool things about this is that it actually provides a networking view. The networking view actually lists all of the asset requests that your module has made through Chrome over the lifetime of its application. So you can actually see, hey, am I loading my zip file? Am I loading my audio data? How long does it take to fetch that? Can I change anything to make that faster? Can I bundle things up to make that easier? These are sort of a quintessential tools that you need to be using if you're starting to develop inside of Chrome, especially the console tab, which will tell you a lot of errors that native client spits out that you may not be able to catch in other fashions. Another amazing tool is About Tracing. So if you open up Chrome and you create a new tab and you type in the address bar About Tracing, it'll take you to this great API here, which effectively is an inline profiler view of Chrome, right? So it actually shows you what thread is running and what blocks of time is running there. And it allows you to drill down to actually get the name of the function being called. The best part about this is you can actually issue data into about tracing from JavaScript or subsequently native client. And the even cooler thing about this is, see that little load button over there? You can write out an inline profile. So for those of you who have inline profilers that already exist in your game, you can modify it to output a JSON file that matches what this tool uses, and use Chrome to do all of the profiling in your game, right? It's an entire tool that allows you to get all this progress and availability to you free of charge. You don't have to write the UI, you don't have to do that. We got a guy dedicated to writing this. Use this tool, it's amazing to see. Google Stack. So now we've talked about what the ecosystem is and all this other stuff, so let's talk about what Google can do to help you with this. So you've got your game, right? You can serve your content, your database information off of Google App Engine. So this is basically your database handling and your asset distribution. We have the Chrome Web Store that we've already sort of talked about and touched on, which handles distribution and discovery. You also need to install your native client apps from there to whitelist them. We've got Google Wallet, which helps you monetize through in-app payments and everything else along those lines. Once you've got all that, you're eventually going to want some sort of social graph so that people can detect and move between friends and submit information. We've got Google+. And then finally, we've got Google Analytics, which is an amazingly powerful tool that allows you to detect what your users are doing, how they're doing it, and kick off events to match that. Now, definitely check out my other talk today on best practices in developing a web application to do a deep dive on the way to properly use these for your web game. Check it out, leave comments. I highly appreciate it. That's all for me. Make sure you check out gonacl.com for the best information available, and then you can find me on all of these different places, especially mainroach.blogspot.com. So hey, thank you for your time. Appreciate your comments. Drop me a line. I'd love to hear from you. Thank you.